Welcome back, everyone. This is the Deep Dive, and today we are actually wrapping up our four-part series on essential radiation physics calculations.
That's right. We've laid down the groundwork, covering radioactive decay, detector basics, machine output, standard dosimetry.
All the fundamentals. And now we're really pushing into those calculations you absolutely need to understand to handle, well, the complexities of real patients and actual clinical practice.
Yeah, exactly. Today's mission really is to tackle those calculations that let us move beyond that simplified uniform water phantom model we often start with.
Okay.
So this means getting into how we account for different tissue densities in dose calculations, understanding how to compare the biological impact of, say, very different treatment schedules.
Which is huge.
Huge. And grappling with the modern ways we specify brachytherapy source strength, and also, critically, doing the calculations needed for radiation protection and safety. That's key.
It sounds like it's really about taking those physics principles we've learned and applying them directly to the situations, well, you'll face every day in the clinic. And let's be honest, on your board exams, too.
Absolutely. Board exams included.
So the goal here is to break down these concepts, these calculation workflows, step by step, make sure you feel confident actually using them. Let's just jump right in.
Sounds good.
So, okay, when we're planning a treatment, a lot of our dose calculation systems, they're built on data that was measured in water, right?
That's the standard reference,
Yeah.
yeah. A water phantom.
But as we all know, patients are, well, they're definitely not uniform tanks of water. I mean, you've got
Yeah.
lungs, bone, air cavities, fat, tissues with really different physical properties, different electron densities.
Wildly different sometimes.
So what happens? What happens when our radiation beams hit these different materials? How does that affect things?
That's a great starting point. When a photon beam, especially, in the energy ranges we typically use in radiotherapy, when it passes through these different tissues, its interaction rate changes.
Okay.
And therefore, its attenuation, how much it weakens, and its energy deposition, how much dose it leaves behind, are different compared to what would happen in water.
Right.
So materials that are less dense than water, the obvious example is lung, they attenuate the beam less, it passes through more easily.
Makes sense.
Denser materials like cortical bone, they attenuate it more, the beam gets stopped more effectively.
So if we just ignore these differences,
Well, if you don't account for this, your dose calculations, especially if you're using maybe older or simpler algorithms that really rely heavily on just depth in water, they're going to be inaccurate, sometimes significantly so.
right. So if a beam goes through lung, it travels effectively further than we'd expect if that same distance was water.
Yeah.
And through bone, it stops sooner or attenuates more quickly.
Exactly. You got it.
How do we quantify this difference? Is there a way to do it that lets us still kind of use our water-based data as a reference?
There is. And that's where this concept of radiological path length, or RPL, becomes really, really useful.
RPL, okay.
Think of RPL this way. You're converting the actual physical path length. The beam travels through all those different tissues.
The geometric distance.
Yeah, the geometric distance. You're converting that into an equivalent path length in water that would cause the same amount of attenuation to the primary beam.
Ah, okay. So it's like, how much water does the beam think it went through based on how much it got weakened?
That's a great way to put it. It's the beam's perspective on its journey. The source material called it the beam's water equivalent detour, which I kind of like.
That helps picture it. Okay, so how do I actually calculate this RPL? Let's say I'm interested in a point inside the patient, and the beam has gone through, I don't know, skin, fat, muscle, maybe some lung.
Okay. You need to basically segment the beam's path. Look at the distinct tissue types it passes through, layer by layer, from the surface down to your point of interest.
Break it down by tissue type.
Right. And for each individual layer along that path, let's call it layer I, you need two key pieces of information.
Okay, what are they?
First, you need the physical thickness of that layer, just how thick it is geometrically along the beam's path. We usually call that sub-I.
Sub-I, physical thickness. Got it. What's the second piece?
The second piece is the electron density of that material, but specifically relative to water. We call this Hor sub-Reli.
Pro sub-Relio, relative electron density.
Yep. It's basically a ratio. Yeah. The number of electrons per unit volume in that tissue divided by the number of electrons per unit volume in water.
Okay, pause there. Why electron density? Why not just use the regular physical density, like grams per cc?
Ah, that's a critical point. For the photon energies we typically use, the megavoltage range in external beam, the main way the photons interact is through Compton scattering.
Right, Compton's dominant.
It is. And Compton scattering happens when a photon bumps into an electron, usually a loosely bound one. The chance of that happening in a material, it's directly related to how many electrons are packed into a given volume of that material.
So more electrons per volume, more Compton scatter?
Exactly. And water has a very well-known consistent electron density. So by comparing the electron density of other tissues relative to water, we get a really good measure of how their Compton scattering properties and thus how they attenuate the primary beam compared to water. It's a very effective proxy for attenuation at these energies.
Got it. Electron density matters because Compton scattering matters, and we compare it to water. Okay, so for each layer I take its physical thickness in sub-ER and multiply it by its relative electron density, rho sub-ERI. What does that product actually represent?
That product, the subicons rho sub-ERI, gives you the water equivalent thickness of that specific layer. It
Ah,
tells you, okay, for this layer of, say, lung, how thick would a layer of water need to be to attenuate the primary beam by the exact same amount?
okay, so I do that calculation thickness times relative electron density for every single layer the beam goes through on its way to my point. Then what?
Then, it's simple addition. To get the total radiological path length, to your point, you just add up the water equivalent thicknesses you calculated for all the layers the beam passed through sequentially.
So the total RPL is the sum of all those T Rayleigh terms.
That's it. RPL. Sum. T really. Simple as that conceptually.
Conceptually simple, but you need those relative electron density values. Are there some key ones we should just, commit to memory?
Oh, absolutely. These are definitely high-yield numbers for exams and just for understanding.
Okay.
Soft tissue and water, well, by definition, they have a relative electron density of about 1.0. Pretty much exactly 1.
One for water and soft tissue? Easy enough.
Lung tissue, because it's mostly airspace, right? It has a much lower density. Typically, its relative electron density is around 0.25 to 0.3. Call it 0.25 for quick estimates.
Okay, 0.25 for lung. Big difference.
Huge difference. And then dense cortical bone. It's mineralized, much denser than water. Its relative electron density is significantly greater than 1, usually somewhere in the range of 1.6 to 1.8.
Wow, 1.6 to 1.8 for dense bone. Okay,
Yeah.
so those are the big three. 1.0 for soft tissue water, roughly 0.25 for lung, and maybe 1.6 or 1.7 for dense bone.
Lock those in. They make a massive difference in the calculation, as you can imagine.
Let's see it in action. Can we walk through that example from the source material that really highlighted the difference?
Sure, let's set it up. Imagine a beam enters the patient. First, it goes through 4 centimeters of soft tissue. Relative electron density is 1.0.
Okay, 4 centimeter tissue, rho QLT is 1.0.
Then immediately after that, it passes through 12 centimeters of lung tissue. And let's say the relative electron density for this lung is 0.25.
Okay, 12 centimeters long, rho epsilon 0.25. And the target point is right after that lung tissue. What's the RPL to that point?
All right, let's break it down. Layer 1. Soft tissue, physical thickness T1 is 4 centimeters. Relative electron density, rho 1, is 1.0.
So the water equivalent thickness is 4 centimeters times 1.0, which is just 4 centimeters.
Easy peasy. 4 centimeters of soft tissue feels like 4 centimeters of water to the beam, attenuation-wise.
Okay, now layer 2, lung.
Layer 2 is lung. Physical thickness T2 is 12 centimeters. Relative electron density, rho 2, is 0.25.
So the water equivalent thickness for the lung layer is 12 centimeters times 0.25.
12 times 0.25, yeah. 1/4 of 12.
That's 3 centimeters.
Perfect. 3 centimeters. So 12 centimeters of lung only attenuates the beam as much as 3 centimeters of water would.
Right. Now the total RPL is the sum.
Yep. To get the total RPL to the point right after the lung, we add the water equivalent thicknesses of the 2 layers.
So 4 centimeters from the tissue plus 3 centimeters from the lung equals a total RPL of 7 centimeters.
That's it. 7 centimeters.
Okay, but let's compare that. The beam physically traveled 4 centimeters plus 12 centimeters. That's 16 centimeters total depth.
Right. Physical depth is 16 centimeters.
But the radiological path length is only 7 centimeters. That's less than half.
It's a dramatic difference, isn't it? And this is where the clinical significance really comes in. Why ignoring this difference could lead to real problems.
Okay, explain that. If I just use this 16 centimeter physical depth in my calculations.
Well, imagine you were using a simpler calculation method, maybe one that relies on looking up dose factors based purely on depth in water, like using a percent depth dose curve, a PDD curve, measured in a water tank.
Okay, using standard PDD data.
If you went to your PDD table or graph and looked up the value for 16 centimeters depth in water, you get a certain percentage. But the beam, in reality, only attenuated as if it went through 7 centimeters of water, not 16.
Right. Water would have attenuated it way more over 16 centimeters than the actual path through tissue and lung did. Didn't get weakened as much.
Exactly. So if you use that PDD value for 16 centimeters in, say, a monitor unit calculation,
Yeah.
you'd be assuming much more attenuation occurred than actually happened.
Which means I think I need more MUs to get the desired dose at depth.
Precisely. You'd overestimate the attenuation. And if you delivered the monitor units you calculated based on that faulty assumption, you'd end up delivering a higher dose than you intended to the structures beyond that low-density lung tissue.
Ooh, okay. So if there were critical organs just past the lung.
Yeah, imagine the spinal cord, or the heart, sitting just behind a large volume of lung you're treating through. Understanding and accounting for this effect is absolutely critical for avoiding unexpected, potentially dangerous high doses to those structures.
And I assume the opposite problem happens with high-density stuff like bone.
Absolutely the same logic, just flipped. If the beam goes through dense bone, say we're local, it's 1.6, its RPL through that bone layer would be greater than the physical thickness 1.6.
Right.
If you ignored the bone and just used the physical depth, you'd underestimate the attenuation that actually occurred. You'd think the beam penetrated further than it did.
So I'd likely underdose anything behind the bone.
You got it. You might underdose your target if part of it lies distal to that dense bone.
So even though our modern treatment planning systems, or TPS, use much more sophisticated algorithms now, like convolution superposition or Monte Carlo, that handle these inhomogeneities directly.
You're right. They do it voxel by voxel usually.
Understanding RPL still gives you that vital kind of first-order correction. It helps you understand why the dose distribution looks the way it does, especially near interfaces.
Absolutely. It's fundamental for understanding the physics, for doing quick checks, for appreciating why a plan looks the way it does. It's about translating anatomy into the beam's effective attenuation path. Essential concept.
Okay. That makes a lot of sense.
Hmm.
Let's switch gears pretty significantly now. Let's talk about biology and fractionation. We often hear about different treatment schedules. You know, the standard maybe 60 gray and 30 fractions, 2 grays per day.
Conventional fractionation, yeah.
Versus, say, hypofractionation. Maybe SBRT with like 45 gray and just 3 fractions or 5 fractions. Huge doses per fraction.
Dramatically different, yeah. 15 gray per fraction in that example.
The total doses are different. The fraction sizes are obviously way different. How on earth do we compare the biological impact of these schedules? Is 45 and 3 more or less effective than 60 and 30?
That is the million-dollar question, isn't it? And this is exactly where the linear quadratic model, the LQ model, and the calculations derive from it, like biological effective dose, BED, and equivalent dose in 2 gray fractions, EQD2, become absolutely indispensable.
Okay, BED and EQD2.
We could call this section fractionation forensics, maybe?
Yeah.
Because just comparing the total physical dose, like 60 versus 45 gray, it's just insufficient. It doesn't tell the whole story because the biological effect, cell killing, is highly dependent on the size of each individual dose fraction, not just the total accumulation. This ties into things like sublethal damage repair between fractions.
And the key parameter that kind of governs this sensitivity to fraction size, that's the alpha-beta ratio, right?
Bingo. The alpha-beta ratio is the linchpin here. It's absolutely critical. It comes directly from the LQ model equation for cell survival.
Remind me what alpha and beta represent again?
Sure. So in the LQ model, cell survival S is given by S, E, alpha D, beta D2, where D is the dose. Alpha represents the linear component of cell killing proportional to dose. It's often thought of as representing like single-hit, non-repairable lethal damage.
Okay. Alpha is linear, single-hit damage.
And beta represents the quadratic component, proportional to dose squared. This is often thought to represent the accumulation of sublethal damage events that can interact to become lethal, or miss repair processes.
Beta is quadratic sublethal damage interaction.
Exactly. And the ratio of alpha to beta, that alpha-beta value, determines the shape of the cell survival curve, particularly how much it bends downwards at clinically relevant doses per fraction. It tells you the relative importance of that linear versus quadratic component for a given tissue.
And different tissues have different alpha-beta ratios, which is the crucial part clinically.
Profoundly important difference, yes. We generally categorize tissues based on this. Tissues and tumors with a high alpha-beta ratio, typically around 10 gray, maybe ranging 7 to 12 gray or so.
Okay, alpha beta of 10 day.
Their survival curve is more linear, meaning that alpha component, the single hit damage, dominates more. This group includes most tumors, actually, and also acutely responding normal tissues. Think skin, mucosa, hematopoietic stem cells, things that turn over quickly.
So tumors in acute tissues are often high alpha beta, around 10J. What does that mean for fractionation?
It means these tissues are relatively less sensitive to changes in fraction size. Because the linear component dominates, doubling the dose per fraction doesn't cause a disproportionately large increase in cell killing compared to what you'd see in low alpha beta tissues.
Okay, high alpha beta 10 means less sensitive to fraction size changes. What about the other group?
The other group is tissues with a low alpha beta ratio, typically around 3 gray, maybe ranging from 1 to 5 gray in reality.
Low alpha beta, around 3G.
Their survival curves have more pronounced curvature. That beta component, the quadratic term related to sublethal damage and repair, plays a much larger relative role. And these are your classic late-responding normal tissues.
The ones we worry about for long-term side effects.
Exactly. Spinal cord, lung for late effects like fibrosis, kidney, bowel, subcutaneous tissue. These tend to have low alpha beta ratios.
So what does the low alpha beta mean for fraction size?
It means these tissues are very sensitive to fraction size. Because that quadratic term is more important, delivering dose in larger fractions causes a disproportionately greater amount of damage compared to delivering the same total dose in smaller fractions.
So using bigger fractions hits these low alpha beta late responding tissues harder, biologically speaking, than it hits the high alpha beta tissues relative to using small fractions.
That's precisely it. This is the fundamental biological rationale behind why hypofractionation, using those larger fraction sizes, carries a potentially higher risk of late normal tissue toxicity unless the total physical dose is appropriately reduced to compensate. It's all about exploiting that differential sensitivity based on the alpha-beta ratio.
Understanding alpha beta is clearly fundamental. Okay, let's quantify this. How do we use the LQ model and the alpha beta ratio to actually calculate biological effective dose, BED? What is BED?
So BED is a calculated value, a metric that tries to represent the total biological damage or the total biological effect from a specific radiation schedule delivered to a specific tissue with a known alpha-beta ratio. It's important to remember, it's a theoretical biological measure, not a physical dose.
Not physical dose, but biological effect. What do I need to calculate?
You need 3 things. The total physical dose delivered in the schedule, I call that D total. You need the physical dose delivered per fraction, usually denoted D, and you need the alpha-beta ratio for the specific tissue or effect you're interested in.
D total, D, and alpha beta. What's the formula?
The formula is BD equals the total dose, D total multiplied by, open parenthesis, 1 plus the dose per fraction D divided by the alpha-beta ratio, close parenthesis.
Okay, let me say that back. BED equals D total, 1 plus D alpha beta.
Perfect. That's the one.
And what about the units for BE? Are they just gray?
Well, they look like gray, but they're often written with a subscript to remind you which alpha-beta ratio is used. So you might see gray sub 10, or GO if you use an alpha-beta of 10 gray, or GO if you use 3 gray.
Okay. That subscript is important context.
It's essential because the BED value is completely dependent on the alpha-beta you plugged in. A BED of 70 GOs means something very different from a BED of 70 GOs. It's tissue-specific and schedule-specific.
Got it. Now, what about EQD2? That sounds maybe more clinically practical?
It often is, yeah.
Yeah.
EQD2 stands for the equivalent dose delivered in 2 gray fractions.
Okay.
This calculation answers a very useful question. If I were to deliver this same biological effect, the same BED, using a standard schedule of 2 gray fractions per day, what would the total physical dose of that schedule need to be?
So it converts any weird schedule back into a familiar currency, the equivalent total dose if it had been given in 2G fractions.
Exactly. It provides a common reference point. It lets you compare the biological impact of, say, a hypofractionated SBRT schedule directly to a conventional fractionation schedule, both expressed in terms of the equivalent dose in 2 CAF fractions. Super useful for comparisons.
How do we calculate it? Do we need BED first?
You can think of it that way. You're essentially calculating the BED for your schedule and then rearranging the BED formula to solve for the D total that would give you that same BED if the dose per fraction was set to 2 grays.
Okay, what's the direct formula for EQD2?
The formula is EQD2 equals the total dose from your schedule, D total, multiplied by a conversion factor or ratio.
Okay, what's the ratio?
The numerator of the ratio is the dose per fraction from your schedule plus the alpha-beta ratio. The denominator is a 2 gray for the standard fraction size plus the same alpha-beta ratio.
Let me try that. EQD 2 equals D total times,
Mm-hmm.
open bracket,
Yeah.
in the top D plus alpha beta, and in the bottom 2 plus alpha beta, close bracket.
You nailed it. EQD 2 plus alpha-beta, 2 plus alpha-beta.
And again, I assume the choice of alpha beta ratio here is absolutely critical.
Paramount. Just like with BED, the EQD2 value you calculate will be completely different depending on whether you plug in an alpha-beta of 10 for tumor effect or an alpha-beta of 3 for late tissue toxicity. You must use the ratio appropriate for the specific biological endpoint you're evaluating.
Let's make this concrete with that example from the source. It really drove the point home. So scenario. A treatment delivers a total dose of 45 gray in 15 fractions.
Okay, 45 gray in 15 fractions. First step.
Calculate the dose per fraction. DA 45 gray divided by 15 fractions is 3 gray per fraction, so D equals 3G.
Good. Now, let's assume we're worried about the effect of this schedule on a late-responding normal tissue, like maybe the spinal cord nearby. These tissues have a low alpha-beta ratio. Let's use an alpha-beta of 3 gray for this calculation.
Okay, D total 45 GG, D equals 3J, alpha beta equal 3J. We want the EQD2 for this late tissue.
Right. Plug into the formula.
EQD2 equals 45 GJ, D plus alpha beta, 2 plus alpha beta.
EQD2 equals 45G, 3G plus 3G, 2G plus 3G.
Okay, simplify inside the brackets. The top is 3 plus 3 equals 6G. The bottom is 2 plus 3 equals 5GJ.
So EQD2 equals 45G6G, 5GG. The gray units cancel inside the bracket.
Right, it becomes a unitless ratio. 6 divided by 5 is 1.2.
Yep. So EQD2 equals 45GG 1.2.
45 times 1.2. 45 plus 9, 54. 54 gray.
Correct. EQD2 is 54 gray.
So what does this mean? This schedule of 45 gray delivered in 3 gray fractions is biologically equivalent, specifically for this late responding tissue with an alpha beta of 3, to delivering 54 gray in standard 2 gray fractions.
That's the interpretation. Look at that result. The physical dose was only 45 gray, but the EQD2, the biologically equivalent dose in 2 G fractions for this sensitive tissue, is 54 gray.
It's hotter biologically for this tissue than the physical dose suggests when compared to 2 G fractions.
Exactly. It demonstrates clearly that using larger fractions, like 3 gray here, causes proportionally more biological damage to these low alpha-beta late-responding tissues compared to using standard 2 gray fractions to achieve the same physical dose.
That's a really powerful illustration, and it explains why dose constraints for organs like the spinal cord are often lower in terms of physical dose for hypofractionated regimens.
It's precisely because of this differential effect captured by the EQD2 calculation using a low alpha-beta.
Just to really nail this down, let's quickly do the same calculation, same physical schedule, 45G in 15 fractions, D3GG. But this time, let's calculate the EQD2 for the tumor, assuming the tumor has a high alpha-beta ratio, say 10 gray.
Okay, good contrast. Same formula. D total equal 45G, D equal 3G, but now alpha-beta equals 10J.
EQD2 equals 45GG, 2J plus 10J.
2J plus 10G.
Numerator is 3 plus 10 divided by 12.
Yeah.
Denominator is 2 plus 10 equal 12J.
So EQD2 equals 45G, 13G, 12G, 13 divided by 12.
Is a bit more than 1, like 1.08 something.
Yeah, but 1.083. So EQD2 equals 45GG, 1.083.
45 times roughly 1.08. It'll a bit more than 45, maybe around 48, 49, let's see. 45, 1.083 is about 48.7 gray.
Right, around 48.7 gray. Now stop and compare. Same physical schedule. 45 gray in 15 fractions. For the late tissue, alpha beta 3, the EQD2 was 54 gray.
Right.
For the tumor, alpha beta 10, the EQD2 is only 48.7 gray.
Wow. So compared to the 2GI fraction standard, that same schedule is biologically much more potent for the late tissue, EQD2 equals 54, than it is for the tumor, EQD2 equals 48.7.
Exactly. This highlights the potential therapeutic gain from hypofractionation if the tumor has a high alpha beta and the dose-limiting normal tissues have a low alpha beta. You might achieve a similar or slightly lower biological effect on the tumor compared to conventional fractionation, while potentially causing a significantly larger biological effect on the late-responding normal tissues unless you adjust the total dose down appropriately.
Understanding BED and EQD2 is clearly crucial for making informed decisions about fractionation, comparing schedules, assessing risks, moving way beyond just looking at the total physical dose number.
They are essential tools in the radiation oncologist's toolkit, no question.
Okay. Another major shift now. Let's talk about brachytherapy.
Placing the radiation sources right where you need them.
Exactly. Sealed radioactive sources placed inside or very close to the tumor. This is a whole different ballgame for dosimetry compared to external beam. How do we even start to specify the strength of these tiny sources? And then how do we calculate the dose around them?
Yeah, it's definitely different. Modern brachytherapy dosimetry follows a very specific, standardized approach. It was largely developed and formalized by the AAPM, the American Association of Physicists in Medicine.
The APM, yeah.
The standard quantity that we use today to specify how strong a brachytherapy source is called Air Kerma Strength. It's denoted S sub K, or just SK.
Air Kerma Strength, SK. That's the key term for source strength.
That's the one. And the system, the framework for calculating the actual dose in water, which we use as a surrogate for tissue, around these sources, starting from their SK, is called the AAPM TG43 formalism, TG43.
Okay, SK for strength, TG43 for dose calculation. Let's unpack SK first. Air Kerma Strength. What is it based on?
It's based, as the name suggests, on the air Kerma rate that the source produces, measured in air.
Air Kerma. Remind me what that is again?
Air Kerma is basically the energy transferred from the uncharged ionizing radiation, like the photons coming from the brachy source, and the charged particles, the electrons, in a small volume of air divided by the mass of that air. It's energy released per unit mass of air. So air Kerma rate is just that energy transfer per unit mass per unit time, usually per hour for brachytherapy.
Okay, energy transfer to electrons in air per mass per time. How is SK defined using this Air Kerma rate?
SK is defined very precisely based on a measurement of the Air Kerma rate under specific reference conditions. The measurement is taken at a distance of 1 meter from the source center. And critically, it's measured in free space, meaning far away from any scattering objects, just the source in air.
1 meter in air, no scatter.
Right. The definition is Air Kerma Strength, SK, equals the Air Kerma rate measured at that 1 meter distance multiplied by the square of that distance. So times 1 meter, too.
SK, Air Kerma rate at 1 meter, 1 meter, 2. Why multiply by the distance squared? Doesn't that seem counterintuitive?
It seems a bit weird at first, but it's essentially removing the effect of the inverse square law fall-off out to 1 meter. By multiplying the rate at 1 meter by 1 meter squared, you get a quantity that's characteristic of the source's total photon emission, independent of that specific measurement distance. It standardizes the source strand specification.
Ah, okay. It standardizes it back to the source itself, removing the 1 air 2 effect out to 1 meter. What are the units for SK?
The standard formal unit for Air Kerma Strength is the U, just the letter U.
The U. Okay, what does U stand for?
1 U is defined as 1 microgray meter squared per hour.
Microgray meter squared per hour. That's an unusual unit combination.
It is, but it comes directly from the definition. Air Kerma rate at 1 meter in AJ, 1 meter's 2. You'll see SKK values quoted in U all the time in brachytherapy.
Okay, get used to U issues and AOC. Is there any, easier way to think about that unit?
There's a useful approximate conversion that sometimes helps to relate it to more familiar dose units. 1 U is approximately equal to 1 centimeter squared per hour. That is the ACF. That's not the formal definition, but it's a close numerical approximation that can be handy sometimes.
1 U, SAA, YOAV, OCMH. Okay, that might help ballpark things. Now, the crucial calculation. If I know the SK of a source, maybe the manufacturer tells me it's, say, 8,000 U. How do I find the Air Kerma rate at a different distance, like, say, at 20 centimeters away from the source?
Okay, this is a super common calculation, and it uses the inverse square law. But you have to be really careful with the units because of how SK is defined.
Inverse square law, careful with units. K.air equals SKD2. That looks just like the standard inverse square law we know. Where's the catch?
The catch is the units of D. Remember, SK is defined in U, which is microgray meter squared per hour. Because SK has meters squared built into its units, when you use that formula K.air equals SKD2, the distance they dot must be plugged in using units of meters.
Ah, meters, not centimeters.
Absolutely. If you're given a distance in centimeters, like your 20 centimeter example, you must convert it to meters before you square it in the denominator. If you forget and plug in 20 instead of 0.2, your answer will be off by a factor of 100 squared, which is 10,000.
10,000. Okay, that's a huge error. Always convert distance D to meters before using K.air equals SKD2 when SK is in U. Burn that into memory.
Please do. It's one of the most common mistakes people make on exams with this stuff.
Okay, let's do that example then. SK is 8,000 U. We want the Air Kerma rate at 20 centimeters.
Step 1. Convert the distance to meters. 20 centimeters is
0.2 meters.
Perfect. Now, step 2. Apply the formula. Air Kerma rate equals SKD2.
So air Kerma rate equals 8,000 U, zero point 0.2 meters 2.
Good. Now calculate the denominator. 0.2 squared is...
0.2 times 0.2 is 0.04, so zero point 0.2 meters 2, 0.04 meters 2.
Right. So we have air Kerma rate equals 8,000 U 0.04 meters 2. Now remember, U is decay.
Okay, so air Kerma rate equals 8,000 U, 0.04 meters 2. The meters squared will cancel out.
Exactly, leaving you with units of microgray per hour, which makes sense for an air Kerma rate. Now just do the division. 8,000 divided by 0.04.
8,000 divided by 4 hundredths, that's the same as 8,000 multiplied by 100 over 4, or 8,000 times 25, 200,000.
Spot on. 200,000 microgray per hour. That's the air Kerma rate at 20 centimeters from that source.
200,000 anger rate. Got it. And the key was converting centimeters to M first. Now, you mentioned the TG43 formalism is how we get from SK to actual dose in water. What's involved there? Do we need to know all the details?
You probably don't need to be able to calculate dose from scratch using the full TG43 equation for most exams, but you absolutely need to understand the concept and the components.
Okay, what are the components?
TG43 provides the complete recipe to calculate the dose rate in water at any point around the source, specified by its distance, r, and angle theta relative to the source axis. The full formula looks something like dose rate r, there you go, GRF. Yeah, agree. Looks complicated, I know.
Yeah, that's a lot of factors. SK is the start. What's lambda?
Lambda is the dose rate constant. It's basically the conversion factor that links the Air Kerma strength, measured in air at 1 meter, to the dose rate in water at a specific reference point very close to the source, usually at r1 centimeter on the transverse axis, 90 degrees. It accounts for the fundamental difference between Air Kerma in air and dose rate in water right near the source.
Okay, lambda converts SK to dose rate in water at 1 centimeter. What about the other factors, G, G, F?
They handle all the real-world complexities that simple inverse square law doesn't capture when the source is inside water or tissue.
Like what?
GR is the geometry factor. It corrects for the fact that the source isn't a perfect point source. It has a finite size and shape. It accounts for how the 102 dependence changes based on the source's actual geometry. It's often compared to a reference geometry, GR, UR.
Okay, geometry corrects for source shape. What about GR?
GR is the radial dose function. It describes how the dose rate falls off with distance r along the transverse axis, 90 degrees, relative to the inverse square law fall-off predicted by the geometry factor alone. It accounts for the effects of photon scattering and attenuation in the water medium itself.
So GR handles scatter and attenuation in water. FRR is the anisotropy function. It describes how the dose rate varies with angle theta around the source, relative to the dose rate on the transverse axis at the same distance argon. It accounts for things like self-absorption within the source material itself and filtration by the source capsule, which are often different along the source axis versus perpendicular to it.
So anisotropy handles the dose variation around the source at a given distance. Exactly. So while you likely won't need to piece together that whole formula and plug in values for G, G, and F from tables, you should understand that TG43 starts with SK, uses lambda to get to dose rate in water at a reference point, and then uses these other factors, geometry, radial dose, and anisotropy, to correct for the real-world physics of the source's shape and its interactions within the water medium to give you the accurate dose rate anywhere around the source.
Got it. Know SK, its units, how to use it for Air Kerma rate, distance in meters, and know that TG43 adds factors for geometry, water scatter attenuation, and anisotropy to get the dose rate in water.
That's the core knowledge for boards.
Clinically, why is this whole SK and TG43 system so important for brachytherapy? Why does it matter?
Oh, it's absolutely fundamental to safe and effective brachytherapy. First, using a standardized strength specification like SK ensures consistency. A source with a certain SK value should behave the same way, regardless of who made it or where you bought it. That's crucial for quality assurance.
Right, consistency and source strength.
Second, the TG43 formalism, with all those correction factors derived from careful measurements and calculations, is what allows treatment planning systems to accurately predict the complex 3D dose distribution around the sources inside the patient, approximated as water.
And that accuracy is critical because
in brachytherapy, doses fall off incredibly rapidly with distance that inverse square law is powerful at short distances. Sources are often placed millimeters away from critical normal structures like the rectum, bladder, or urethra. Even a small error in dose calculation could lead to significant underdosing of the tumor or severe overdosing of nearby normal tissues. TG43 provides the validated framework needed to achieve the high degree of dosimetric accuracy required for these treatments. It lets us confidently translate the source strength, SK, into a precise dose delivered where it needs to go.
Precision is everything when the radiation source is right next door to sensitive organs. Okay, makes sense. All right, let's tackle our final calculation topic for this series, radiation protection. This isn't just about the dose to the tumor. It's about ensuring the safety of, well, everyone involved or nearby. Staff, the public, even the patient from unnecessary exposure outside the target.
Couldn't be more important. Radiation protection calculations are all about ensuring safety. Usually this means figuring out how much shielding is needed to reduce radiation levels to acceptable limits, or checking if the radiation levels in a certain area comply with regulatory dose limits, keeping exposures as low as reasonably achievable LRO.
LRO, right. And the core concepts we use to describe how well materials block radiation are half-value layers and tenth-value layers.
Exactly. Half-value layers, HVLs, and tenth-value layers, TVLs. They're practical measures of attenuation.
Define them for us again.
An HVL is the thickness of a specific shielding material like lead or concrete that's needed to reduce the intensity or dose rate of a particular radiation beam by half, down to 50% or a factor of 0.5.
One HVL cuts intensity in half, and a TVL.
A TVL is the thickness of that same material needed to reduce the intensity or dose rate by a factor of 10, down to 10% or 0.1 of its original value.
One TVL cuts intensity to 1/10.
And these values, the HVL and TVL, they depend on both the shielding material and the energy or quality of the radiation beam. Higher energy beams generally need thicker shields, so they have larger HVLs and TVLs.
Makes sense. So if I put up a shield that's 1 HVL thick, the intensity drops by half. If I add another HVL thickness, making it 2 HVLs total,
Then the intensity drops by half again. So 2 HVLs reduce it to 1/2 times 1/2, which is 1/4 0.25 of the original.
and 3 HVLs would reduce it to 1/8, 0.125, 4 HVLs to 1/16, 0.0625, and so on. Each HVL cuts the remaining intensity by half.
Precisely. Same logic for TVLs. 2 TVLs reduce intensity to 1/10 times 1/10, which is 100th, 0.01. 3 TVLs reduce it to 1,000th, 0.001.
Is there a relationship between HVLs and TVLs for the same material and energy?
Yes, there is. 1 TVL is approximately equal to 3.32 HVLs.
1 TVLs at 3.32 HVLs. Where does that number come from?
It comes from logarithms. Specifically, how many times do you have to multiply 0.5 by itself, or raise 2 to a power, to get 0.1, or 10? 2 raised to the power 3.32 is almost exactly 10. So you need about 3.32 half reductions to get 1 tenfold reduction. It's a handy conversion factor to remember.
3.32 HVLs per TVL. Okay. How do we actually use HVLs or TVLs in calculations, say, to find out how much radiation gets through a shield of a certain thickness?
We use the concept of transmission, often denoted T. Transmission is just a fraction of the initial radiation intensity, I0, that makes it through the shield, I, so T, IK0.
Okay, transmission T, IIC. How does it relate to thickness X and HVL or TVL?
Through exponential formulas. If you know the HVL, the transmission T through a shield of thickness X is given by T equals 0.5 raised to the power of X divided by the HVL value. T equals 0.5 X HVL.
T equals 0.5 to the power, the number of HVLs. Makes sense. What about using TVLs?
If you know the TVL, the formula is transmission T equals 10 raised to the power of negative X divided by the TVL value. T equals 10, next X TVL.
T equals 10 to the power of negative number of TVLs.
Got it. So those let you find the transmission if you know the thickness. But often the problem is the other way around, right? You know how much you need to reduce the radiation, and you need to find out how thick the shield needs to be.
Exactly. That's the much more common scenario in practice, like when designing a vault or checking shielding adequacy. The goal is to find the required thickness X.
How do we approach that? What are the steps?
It's usually a 3-step process. Step 1. Determine the required reduction factor, RF. This is how much you need to decrease the dose rate or intensity.
How do I calculate the reduction factor?
You take the initial dose rate, what you have now, and divide it by the allowed or target dose rate, which you need to get down to, usually based on regulatory limits. RF, initial rate, allowed rate.
Okay, RF, initial allowed. Also, notice that the reduction factor is just the inverse of the transmission you need. If you need to reduce by a factor of 100, the required transmission is 1100, or 0.01. So RF equals 1T.
Okay, calculate the reduction factor needed. Step 1. What's step 2?
Step 2 is to figure out how many tenth value layers or how many half value layers are required to achieve that reduction factor.
How do I find the number of layers?
Using logarithms. If you're working with TVLs, the number of TVLs needed is the base 10 logarithm of the reduction factor. And log yours RF.
Number of TVLs, log base 10 of the reduction factor.
Yeah.
Okay, what if I'm using HVLs?
If you're working with HVLs, the number of HVLs needed, N, is the base 2 logarithm of the reduction factor. N is log base 2.
Log base 2? My calculator might not have that button. Is there another way?
Yes, you can calculate the log base 2 using natural logarithms, ln, which most calculators have.
Yep.
Log base 2 of RF is equal to the natural log of RF divided by the natural log of 2, n ln RF, ln2, and ln2 is about 0.693.
Okay, so find the reduction factor, then find the number of TVLs, M with log RF, or HVLs, N, ln, RF, ln2 needed. What's the final step?
Step 3 is simple multiplication. To get the required shield thickness X, you multiply the number of layers, M or N, by the known TVL or HVL value for that specific material and radiation energy.
So required thickness X equals M TVL if using TVLs, or X equals N HVL if using HVLs.
Exactly. That's the workflow.
Let's try that with the example from the source material. We need to shield an area to reduce the dose rate from 0.1 millisievert per hour down to 0.02 millisievert per hour.
Okay, initial rate equals 0.1 millisievert per hour. Okay, initial rate equals 0.1 milli-ZAG. Allowed rate equal 0.02 milli-VH.
We're using concrete for shielding, and we're told the TVL for this radiation in concrete is 35 centimeters. We need to find the required thickness of concrete.
All right, step 1, calculate the reduction factor.
RF, initial rate allowed rate equal 0.1 milli-VH, that's 0.02 milli-VH. The units cancel. 0.1 divided by 0.02. That's the same as 10 divided by 2, which is 5.
Good. The reduction factor needed is 5. We need to reduce the dose rate by a factor of 5. Step 2. We're given the TVL, so let's find the number of TVLs needed.
Okay, M log base 10 of the reduction factor. M go 5. I might need a calculator for that. Log base 10 of 5 is approximately 0.7.
Yep, that's close enough. Log euro, 0.699, so about 0.7 TVLs are needed.
So we need less than 1 TVL, which makes sense because 1 TVL would reduce by a factor of 10, and we only need a factor of 5 reduction.
Exactly. Now, step 3, calculate the required thickness X. We need 0.7 TVLs, and the TVL value for concrete is 35 centimeters.
So required thickness X is MTVL equals 0.735 centimeters.
0.7 times 35.
Let's see. 0.7 is 710. 735 equals 245. 245, 10 equals 24.5. So 24.5 centimeter.
Excellent. You need 24.5 centimeters of concrete to achieve that factor of 5 reduction in dose rate. That's a typical shielding calculation.
Okay, that workflow seems manageable. RF, then number of layers using logs, then thickness. Now, besides calculating shielding, the other big part of radiation protection math is just checking compliance with dose limits.
Yes, and those calculations often involve using the results from shielding calculations or using the inverse square law or maybe radioactive decay formulas to estimate the dose rate or total dose in a particular location and then comparing that number to the regulatory limit.
Right, you mentioned the inverse square law earlier. Remind us of that again quickly.
Sure. For a point source of radiation, the intensity or dose rate decreases with the square of the distance. If you know the dose rate at distance d, the dose rate at distance d is given by dose rate. Thus, double the distance, the dose rate drops to 1/4. Triple the distance, it drops to 1/9. Distance is a powerful protection factor.
Distance is your friend, and units are important again here, especially when comparing to limits.
Absolutely. Regulatory dose limits are almost always given in units of equivalent dose or effective dose, which are sieverts, SV, or millisieverts, MSV. Remember, 1 sievert equals 100 rem, and 1 millisievert equals 100 millirem.
And for the photons and electrons we typically deal with in radiation oncology.
For photons and electrons, the radiation weighting factor, WR, is 1. So for these types of radiation, 1 gray of absorbed dose is numerically equal to 1 sievert of equivalent dose. That simplifies things a bit for us usually. 1 sievert, 1 sievert SV for photons, electrons.
Okay, so if I need to check if a situation meets regulatory limits, what's the process?
It's pretty straightforward, really a 3-step comparison. Step 1, identify the relevant regulatory dose limit. This is crucial. Who's being exposed?
Right.
Is it an occupational radiation worker in a designated controlled area? Is it a member of the general public in an unrestricted area? Is it a declared pregnant worker where we need to consider the dose to the fetus? The limits are very different for these categories. You have to know which limit applies.
Know the specific limit for the specific person or area.
Oh yeah, these are must-know numbers. Commit these to memory right now.
Lay them on us.
For an adult occupational radiation worker, the annual limit for whole-body effective dose is 50 millisievert 50 millisievert.
50 millisV occupational, okay.
For a member of the general public, or for the dose limit to an unrestricted area that the public can access, the annual limit is much lower. 1 millisievert. 1 millisievert.
1 millisV, public and restricted. Big difference.
Huge difference. And for the fetus of a declared pregnant occupational worker, the dose limit over the entire gestation period, roughly 9 months, is 5 millisievert.
5 millisV total for the fetus over the whole pregnancy. Okay, let's recap those. 50 millisV occupational annual, 1 millisV public annual, 5 millisV fetal over gestation.
Lock those in. You will be asked about them.
Why is understanding all this radiation protection, math, shielding, inverse square limits, why is it so crucial for us as residents or oncologists? It feels a bit removed from treating the tumor sometimes.
It might feel removed, but it's absolutely fundamental to practicing safely and responsibly. This math isn't just theoretical, it's directly tied to how we design our facilities, how we implement safety protocols, and how we ensure compliance.
Like designing the vault walls.
Exactly.
Yeah.
Shielding calculations determine how thick those concrete walls need to be to protect people outside. You need to understand inverse square law to know safe distances from patients who've had brachytherapy implants. You need to know the limits to properly designate controlled versus unrestricted areas.
And for QA and emergencies.
Yes, performing radiation surveys to verify shielding integrity relies on these principles. Knowing how to estimate dose rates is critical if there's an incident, like a source getting stuck. It's essential for designing new facilities, for routine safety checks, for regulatory compliance, and ultimately it's about protecting yourself, your colleagues, your patients from non-therapeutic exposure, and the public. It's a core professional responsibility.
I'm a mental part of the job. Got it.
Truly is.
All right. After covering all that, I think it's time. Let's put ourselves to the test with our board review blitz.
Okay, let's do it. Quick-fire application of these concepts.
Ready. Question 1, based on the source. A treatment plan delivers 60 gray total dose in 30 fractions. First off, what's the dose per fraction D?
60 gray divided by 30 fractions. That's 2 grays per fraction. D yields 2 GJ.
Okay. This is delivered to a tumor assumed to have an alpha-beta ratio of 10 gray. What is the biological effective dose, BED, for this tumor? Your options are A, 60 gray 10, B, 72 gray 10, C, 84 gray 10, or D, 120 gray 10.
Okay, BED formula. BED, D total, 1 plus D alpha beta. We have D total 60 GJ, D equals 2 GJ, and alpha beta 10 G.
Plug them in.
BED, 1 plus 2 J, 10.
2 divided by 10 is 0.2.
So BED equals 60 J, 1 plus 0.2.
That's 60 J, 1.2.
60 times 1.2 is 72. And the units should reflect the alpha beta used, so 72 gray 10.
Yeah, 72 gray 10. That matches option B. Correct. And it makes sense, right? The BED 72 is higher than the physical dose 60 for fractionated treatment.
Yep, reflects the biological impact of fractionation compared to a single dose, captured by the formula using alpha beta.
Nicely done. Question 2 from the source. The Air Kerma Strength SK of a brachytherapy source is 4,000 U. What is the Air Kerma rate at a distance of 2 meters from this source? Options. A, 1,000 microgray per hour, B, 2,000 microgray per hour, C, 4,000 microgray per hour, D, 8,000 microgray per hour.
Okay, this is SK in inverse square law formula. Air Kerma rate yields SK D do. SK is 4,000 U. The distance D is 2 meters.
And crucially is the distance in the right units. SK is in U, which involves meters squared. The distance is given as 2 meters.
Yes, it's already in meters, so no conversion needed this time. We can plug straight in.
Air Kerma rate equals 4,000 U, 2 meters 2.
2 meters squared is 4 meters squared. So rate equals 4,000 U, 4 meters 2. Remember, U is rate Kerma, 4,000, 4 meters squared. The M cancels. 4,000 divided by 4 is 1,000. 1,000 microgray per hour.
1,008. That's option A. Correct again. Straightforward application if you remember the formula and the units.
Exactly. Watch those units.
Final Blitz question number 3 from the source. How many half-value layers, HVLs, are needed to reduce radiation intensity by a factor of 16? Options. A, 2 HVLs, B, 3 HVLs, C, 4 HVLs, D, 5 HVLs.
Okay, we want a reduction factor of 16. This means the transmission T equals 116. We need to find the number of HVLs, let's call it N, such that 0.5 raised to the power of N equals 1/16.
0.5 N equals 1/16. Or you could think of it as, how many times do I need to cut the intensity in half to get down to 1/16 of the original?
Let's try that. 1 HVLs give 12. 2 HVLs give 12. 12 equals 14.
3 HVLs give 14. 12 equals 18.
4 HVLs give 18. 12 give 1/16. There it is.
So an N must be 4. You need 4 half-value layers.
Alternatively, using logs. And logs RF, base 2 is 16. The log base 2 of 16 is 4. Same answer.
4 HVLs. That matches option C. Perfect. These types of calculations are really core skills.
They absolutely are. Practice makes perfect with these.
Okay, that was a great review, Blitz. Now let's try to boil down everything we covered today, all these crucial calculations, into just a few high-yield clinical pearls, the absolute must-remember points.
All right, let's distill it. Pearl number 1, radiological path length, RPL. Remember the concept. It's the sum of physical thickness at each layer, its relative electron density. And remember those key relative electron densities. Lung, 0.25, bone, 1.6 to 1.8, soft tissue water equals 1.0. Use RPL to grasp inhomogeneity effects.
Pearl number 2, biological comparison of schedule. Use BED and EQD2 based on the LQ model and know the formulas. BED, D total 1 plus D alpha beta. And EQD2 equals D total D plus alpha beta, 2 plus alpha beta.
Let's go tip.
Yes, there's a beetle. Your alpha beta ratio is roughly 10G for tumor acute, roughly 3G for late effects. Use the right one for your question.
Pearl number 3, brachytherapy source strength. It's Air Kerma Strength, SK Air, specified in U, which are GM edge. To find Air Kerma rate at distance D, use rate is equal SKD2, and D must be in meters. Remember, TG43 is the full framework using lambda, G, G, and F to get dose in water.
Pearl number 4, shielding calculations. Find the reduction factor, RF, initial allowed. Find the number of TVLs needed, M equals M or F. Calculate thickness, X equals MTVL. Remember, 1 TVL is about 3.32 HVLs.
And pearl number 5, radiation protection dose limits. Know these cold. Occupational annual limit, 50 millisievert. Public annual limit, 1 millisievert, 1 millisv. Fetal limit over gestation, 5 millisievert, 5 millisv. Non-negotiable safety numbers.
Fantastic. Those 5 pearls really capture the essence of today's calculations. Definitely review those often.
Absolutely.
Now, after 4 intense deep dives focused entirely on physics calculations.
Uh-oh, I feel a joke coming on. Probably a physics joke.
You know it. Okay, why did the radiation physicists bring a ladder to their physics board exam?
I don't know. Why did the physicists bring a ladder?
Because they heard the questions were high yield.
Groans, playfully.
Oh.
Oh, boy. That's
Like that?
appropriate, I suppose. It definitely feels like climbing a ladder sometimes, trying to remember all this stuff, especially under pressure.
Exactly. You got to find the humor in it somewhere, right?
You really do. Keeps you sane.
Okay, jokes aside. As we wrap up not just today's session, but this entire 4-part series on physics calculations, let's leave you, our listeners, with a final thought to ponder. Something to chew on. We've covered a lot of calculations today. RPL uses simplified average densities. The LQ model uses average alpha-beta ratios, which we know is a simplification of complex radiobiology. TG43 uses measurements in a uniform water tank to represent a complex patient. Considering all these layers of calculation, approximation, and assumption, how do we, as clinicians, using these tools every day, continuously validate and assure ourselves and our patients that our theoretical calculations are accurately reflecting the incredibly complex, heterogeneous, and dynamic biological and physical reality inside each unique person? How do we bridge that gap between the model and the individual?
That's a profound question. And it really speaks to the heart of clinical physics and radiation oncology. It's about using the best models we have, understanding their inherent limitations, constantly seeking validation through quality assurance, clinical trials, outcome analysis, and always striving to personalize and refine our approach based on that feedback loop. It's the ongoing challenge and responsibility of our field.
Constantly refining and validating. A great thought to end on. Well, that officially concludes our comprehensive 4-part series diving deep into the essential calculations for radiation oncology physics. We covered a massive amount of ground.
We really did, from decay basics right up to these complex clinical and safety calculations. The most important thing you can do now, practice.
Absolutely. The key now is consistent practice. Work through problems using these calculation workflows until they feel like second nature. Don't just read about them, do them.
Repetition is key.
Exactly. And remember, if you're looking for opportunities to practice, especially in an oral board exam-style format, you can find resources over at radoncsmartlearn.com. Let me spell that out how it sounds. radoncsmartlearn.com.
We sincerely hope this series has been helpful in building your understanding and confidence with these really vital physics calculations.
Thank you all so much for joining us throughout this deep dive series. Please be sure to subscribe so you don't miss our next episode, where we'll be launching into a completely new and exciting topic.
Thanks, everyone, for tuning in. Keep calculating.